pleasure to, well, I should say introduce him, but anyway, and he's going to talk about the North Atlantic oscillation.
Thank you very much, John. That leaves me a few more minutes, have a few slides. There are actually two schools on introductions. One introduces the speaker to the audience, but actually, I don't know how many of you knew Gene Golub from Stanford, sort of the author of Golub and Van Loan, the big book on numerical linear algebra and so on. And Gene used to say that it is superfluous introducing the speaker to the audience because obviously they know who he or she is because that's why they are there. So, the other way is to introduce the audience to the speaker, but actually I'm happy to see that I know quite a few people in the audience. And actually, I realized during dinner last night that I thought I had my talk all prepared, but forgotten that actually a couple of papers, one got published and the other one just got accepted last night, so I had to add a few slides, and I hope to get to them forthwith. This is where I am most of the time today. These two ladies are the humanities and the sciences who for some odd reason turn their back to each other. The reasons are aesthetical, and this is where I still spend a substantial fraction of my time and also an even more substantial fraction of my attention by email and other modern means of communication. Actually, so there are two websites. It's this one that has environment in French there, but the one which is more complete, where you typically find reprints and preprints and stuff, is still my research group at UCLA. Doesn't want to. Okay. Sorry. Just have to be more patient. Okay. I do need the glasses, or at least I'm more comfortable with them. So, since I didn't quite know who the audience would be, and I just gave this recently to a mathematical audience, I will say a few words about the North Atlantic oscillation. It's a leading mode of variability of the northern hemisphere and beyond. It affects the atmosphere and oceans on several time and space scales. Its predictive understanding could help interannual and decadal scale climate prediction over and around the North Atlantic basin. For those who are American here know the phrase predictive understanding. That's what you say to the National Research Council if you want money. Okay? I like to point out that, many people say that prediction is difficult. In particular, Mark Twain said predicting is difficult, especially the future. Although predicting the past is also sometimes complicated. Michel Crucifix, for instance, knows something about that. But actually, I think that prediction is very easy. What is difficult is believing the predictions. Okay? So that's where the understanding comes in. The hierarchical modeling approach, one approach to this, of course, is you get a bigger and bigger computer and you spend more and more time programming for it. But the other one is the so-called hierarchical modeling approach, which allows one to give proper weight to understanding provided by the models versus their realism respectively. And you sort of know those diagrams which say, realism increases in this direction and understanding in the opposite one. Back and forth, therefore, between so-called toy models. People who do big models use toy models as an insult. I rather glorify in it. Remember that Einstein said everything ought to be made as simple as possible, but not any simpler. So between toy, or more dignified word for that is conceptual, and detailed models, and I put realistic in quotation marks, because anybody who's looked at the GCM knows that there are so many more parameters which we don't know in a GCM than in a toy model. Okay, and of course between models and data. And this is based on really joint work with a lot of people, and you can find the reprints and so on their websites, as I say. But some of the recent work involves the people explicitly listed here. Okay, so the outline is we're going to talk first about the NAO and the ocean's wind-driven circulation. Okay, some of you might wonder why you would bother, but I hope you'll be sort of intrigued at least through the talk. The low frequency variability of the double gyre, so-called double gyre circulation, bifurcations in a toy model which lead to multiple equilibria, periodic and chaotic solutions, and then some intermediate model results. You know, the intermediate models are the ones in the middle between the toys and the GCMs, which have a little bit of understanding and a little bit of realism, as well as the opposite, okay? So atmospheric impacts, simple and intermediate models, and even GCMs, some data analysis, atmospheric and oceanic, and some very promising. I apologize that the color here on the background doesn't come out very well. Some very promising NAO results, and then conclusions about the coupled climate system. Is it the tail or the dog? I will not hide from you that many oceanographers believe it's the atmosphere that does this. I've always wondered, why typically, well, now this is evolving a little bit, but when I started becoming interested in climate, it was clear that oceanographers were thinking it's the fault of the atmosphere and it's the winds. And the meteorologists thought it's the fault of the ocean, it's the SSTs. It's a little bit like in marriage. It's always the fault of the spouse, okay? So, why wouldn't you be interested in the field? Why wouldn't you believe that what you really do is, it's you who's at fault, not the other person? So, of course, the tail is the atmosphere and the dog is the ocean, okay? So, and then natural climate variability as a source of decadal predictability, question mark. Okay, now, can I just skip this? Everybody knows what the NAO is? Yeah? Yeah? Okay, fine. No? Okay, anybody who doesn't yell? Because
it kind of merges with the Arctic oscillation, doesn't it? The annulus or whatever.
I truly don't believe that, Michael. I can't believe that Mike Wallace, who looks at maps, came up with this. We know so well that what goes on in the Atlantic and in the Pacific is rather distinct. And the coincidence of the two is, on monthly time scales, there is indeed something average that goes up and down in the Northern Hemisphere. And actually, we pointed that out in a paper with Kingtse-Mo in 1988.
Okay, it depends on
but, on shorter time scales, like 10 days, it's truly a big coincidence when there's a block in both the Atlantic and the Pacific. Okay?
Well, this is troposphere, this is mid-troposphere. If you look higher up, it sort of turns into a more annular thing, doesn't it?
Okay, well, if you look high up, things are quite different, as you well know. But on the other hand, that's an even thinner tip of the tail. Okay?
Tail of the tail.
The tail of the tail. Sorry. Okay, well, anyhow, so let me just point out that there is, clearly interannual as well as interdecadal variability, and it does go up and down. That's why it's called an oscillation. Okay.
Just Michael, in case anybody is confused on, this index is constructed from surface pressure data.
That's correct. Yes, it's well, in instrumental data, it's typically, it's basically the difference between the Icelandic low and the Azores high, and you have instrumental data going back typically to the middle of the 19th century, and then people try to reconstruct it further in the past in the usual way by correlating it with stuff. Turns out the Brits were in Gibraltar for a longer time, so you use some Gibraltar data, and God knows what you use in Iceland. And it's really important for European climate because sometimes it goes, storm track sort of goes like this in the positive phase, and it tends to go more like that when you are in the negative phase. And actually, we showed in one of those papers that I mentioned, just coming out in Journal of Climate, that it has a substantial impact on the Middle East. And in the earlier paper, GRL 05, that it even might explain the 14-year periodicity in the Bible. Okay, you know, Joseph's, I mean, the Pharaoh's dream is explained by Joseph and so on.
What?
Huh?
What did you
The
say?
biblical.
The Bible.
Yeah, the Bible.
No wonder I didn't get it.
Yeah. You know, it made quite an ado in, you know, in the U.S. media. Who anytime you say Bible, you know.
What do you mean, the 7 fat and the 7 lean?
That's right.
Oh, I
Yeah. Yeah, those. Yeah. Okay.
Oh, well, back then things really might have been periodic. Who knows?
Well, you know, cycle chasing has a bad reputation, I know, but that's why I'm careful. Okay? So, well, again, this is a wind-driven ocean circulation. That's the one that you learn in kindergarten. You know, they're basically western boundary currents which bring warm water from the tropics towards higher latitudes. And then you also have some cold western boundary currents that bring, you know, cold stuff from the polar regions more towards the mid-latitudes. And a similar thing in the southern hemisphere, although of course in the southern hemisphere, Mr. Coriolis sits, you know, stands on his head. So this is anticyclonic like this is anticyclonic like that, and this is cyclonic like this, and in the southern hemisphere, you don't have the other gyre because what you have instead is the Antarctic circumpolar current. Okay, so, well, these currents are really very important also not just in what happens in the ocean, but in the heat exchange between the ocean and the atmosphere. This is from, oh, what's her first name now? Kelly, forget, sorry. You know, okay, this is where the Kuroshio loses heat to the atmosphere, and that's where the Gulf Stream does so. And there's a lot. There was a special issue of the Journal of Climate and all of this, so I won't insist. There are also sort of explanations that are related to intermediate waters and so on that I won't review at this point, which really have to do less with wind-driven circulation the way we're going to discuss it here. But just to tell you that, you know, this is not the only theory in the land. Now, you know, the previous picture, which in some sense goes back to, you know, people like Ben Franklin, who published that famous map of the Gulf Stream in London, etc. And, you know, even to the Phoenicians and who navigated around Africa and so on for one of the pharaohs. But so this was really conceived as being sort of a steady state circulation, the climatological picture. Now, a big revolution in the 60s and 70s, I guess, was the discovery of much smaller scale variability, the meanders and rings, especially of these western boundary currents, but not alone. And, you know, as a result, much of the focus of physical oceanography over the 70s and 90s has been with this variability, which was called mesoscale, but that's a misnomer because, you know, people originally thought it's about the size of mesoscale eddies in the atmosphere, but these are really synoptic eddies in the ocean, you know, but just because the Rossby radius of deformation in the ocean is about 10 times smaller than in the atmosphere. So, on the one hand, there was a steady state picture, and on the other hand was this sort of turbulent picture. Now, let me just show you, you know, one of the marvels that, aside from big computers, another big important ingredient of late 20th and 21st century oceanography and meteorology is, of course, satellites. And satellite altimetry has allowed us to have really a more synoptic picture of the oceans, These are monthly mean path from altimetry, so out of a paper of Bo Chu with an associate of his. Okay, so monthly mean path, and you see, so these are successive years, these are these spaghetti diagrams, okay? These are successive years, 93, 94, etc. And you see that there are years which are quite stable, persistent, and others which are very agitated.
That means jet core, does it?
That's the axis of the jet, yes, yes. But of course, as seen in altimetry, because of geostrophy, you know, okay, it's a particular isoplet that is selected. Okay, so now this might remind some of you of similar things in the atmosphere. See, in the atmosphere, it was Fred Saunders at MIT and his student Brian Reinhold who introduced these kind of spaghetti diagrams, which they called limited contour analysis. And this is basically work of part of the PhD thesis of Masakimoto. And these are 10-day, you know, these are daily spaghettis over 10 days. So this is one particular winter, again being read like this, 10 and 10 and etc., coming to 90. And you see clearly that, again, you know, what I was saying just before, there very rarely are blocks in both the Atlantic and the Pacific. That's one thing. But the other thing is that, you know, sometimes when it's blocked, you know, the spaghetti stick together, and sometimes all hell breaks loose. So, you know, this suggests that, again, on different, you know, in the ocean, the scale, the spatial scale is smaller, but the time scale is longer, but there is some of the same sorts of things going on. Okay, so this is now, again, Bo Chu. I got this from him at a meeting in January '09 in Phoenix, Arizona, that discussed this western boundary currents. So this is now this, what he calls the Kuroshio extension box. So Ke is not kinetic energy, it's Kuroshio extension. Okay, and again, you see very clearly this is just one mean over the second half of November. You see these meanders, you see the cutoff eddies, okay, and then here you see for the times we've had a satellite up from 1992 to 2009, these successive things. So this is sea surface temperature anomaly in the box. This is sea surface height anomaly. This is the jet axis, and this is the delta H across the Ke jet. And you see that all of these things are pretty well correlated. Okay, so including
and things like the anomaly and NSST and height
are not wonderfully correlated,
okay.
but
those are just area average values?
yes, over this box. So you can't expect. I mean, you know, there are many things going on in the box. You've talked about that a lot last week, right? Okay, so now we're sort of done with the introduction, and I'm going to get into the low frequency variability of this double gyre circulation. Okay, so here is, well, it's more of an intermediate model. You know, it's just not just one or two boxes like when you discuss the thermohaline circulation. You know, it's a reduced gravity shallow water model. So the reduced gravity has to do with the ratio of the densities in the active layer and in the passive layer, which is, you know, idealized this of infinite depth. But this, you know, basically in the oceans is 1 kilometer. This is 10 kilometers. So, you know, 10 is a good approximation for infinity in this business. Okay, and so unlike in shallow water models for the atmosphere, you have basically a forcing term, which is a wind stress, and you have dissipation. So by now, everybody, I hope, in this room knows about bifurcations. You know, typically what happens, you look at the system not for given parameter values, but for parameter values which indicate that you might stress it harder and harder, or you might, calm it, soothe it more and more by increasing this parameter. Okay? So this comes out of a 95 paper, and again, it has 20 kilometer resolution, which oceanographers, call not eddy resolving, but eddy permitting, which is sort of, and so it has 15,000 variables. Okay, and of course these days we can do bifurcation, numerical bifurcation for things like this, or we could even in 95, it's more than the 3 variables or 14 variables of Ed Lorenz in 63. Okay, so now, there's a lovely book about modeling climate by a colleague at Berkeley, John Hart, which is called Consider a Spherical Cow. This is not a spherical ocean, but a rectangular ocean. Okay, so you have an idealized wind stress. I forgot to tell you about that. These are the mid-latitude westerlies, and these are the low and high latitude easterlies, but it's just a sine profile, And so everything is symmetric in this box. This is the line of symmetry of the wind stress curl, and so this is the rectangular box, and of course boundary conditions are symmetric and everything is symmetric. So if you suppress the nonlinear advection terms, you get a nice symmetric circulation. This is the anticyclonic gyre, subtropical, and this is the cyclonic polar gyre. Now, if you reinstate the advection terms, you break the symmetry. I'm actually lying slightly about the perfect symmetry here, but I'm going to come back and correct myself later. Okay, so you break the symmetry and you have an intense recirculation vortex here. Okay, now if you take different initial conditions, you get either this one in which the subtropical gyre dominates, or that one in which the subpolar gyre dominates. However, and I forgot to tell you, these are actual exact equilibria. Nothing moves, okay, for certain parameter values, okay? So again, this is not a toy model, this is not 3 variables, it's 15,000, but it's really exact equilibria.
Are they stable?
Pardon me?
Are they stable equilibria?
Well, we're going to get to that in a moment.
So just to be clear, the top left, so
Uh-huh.
I'm sorry, the top right and
Yes.
the bottom right, are they identical?
No, there are different forcing values, I think. It's what you do. Oh, and what is plotted is the upper layer thickness, H, okay, in those equations. So
This is all steady wind forcing, is it?
this is, yes, it's this profile constant in time, okay?
What you drew on there.
Yeah.
And the nonlinear steady states are found by some Newton iteration or something.
Well, at the time when Shijang did this for his PhD thesis, he just integrated forward. But this work started in the early 90s, okay? And there was an earlier version published in 93 in the proceedings of the AMS of what was at the time Waves and Stability Conference. And, but actually it was only published in 95 because I still wanted to fix an appendix that had to do with boundary conditions that I won't have time to discuss. So, but a little bit later, Henk Dijkstra came to UCLA, okay, and he was working with David Nealon on ENSO, but also became interested in this. And actually, the same year there was a Speich-Dijkstra-Gill paper published in which we did pseudo-Arclength continuation. Henk's contribution was to do pseudo-Arclength continuation for this 2-dimensional problem. He and his buddies can do now, a pseudo-Arclength continuation on 3-dimensional, essentially GCMs. Okay? So, okay, but what we're really interested in is not the existence of multiple equilibria, entertaining that might be, but variability in time. So you take a cross-section through the basin here, and you do the Hofmüller diagram. So you go forward in time, and what you see is here, so this is the dissipation coefficient, and this is the forcing coefficient Okay, you get a nice, perfectly periodic solution, which, however, is not sinusoidal, it's a relaxation oscillation. See very clearly, you know, the core of the jet, the axis moves southward and then comes back, you know, relaxes backward very quickly.
2 years approximately.
Yeah.
2-year period.
Well, this is approximately 3 years, actually 2.8 I'm going to show, but the subsequent results are going to be, I'm going to give it away, 7 to 8 years for constant wind stress. Okay? Now, if you keep the same dissipation, so the same, you know, calming effect, but double the, you know, you blow harder over the waters, this becomes chaotic, and, you know, you have a lot of recirculation here in the subtropical gyre. Okay, now here comes the answer to the question about stability. Obviously, as we all, okay, so what is plotted here is the meridional position of the merging point where, in quotation marks, the Labrador Current and the Gulf Stream join. Okay, so you take again a particular contour and you plot its meridional position. And so here is a steady solution which loses its stability by Hopf bifurcation to a periodic one and then on to a chaotic one. And here you have another branch. Okay, so here you have a region of multiple equilibria. This branch is unstable, this one is stable. Okay, again you have Hopf bifurcation and transition to chaos. Now, oops, I need some chalk. Where is?
Oh, wind stress strength.
Yeah, wind stress strength. Okay. Well, people don't seem to be. Okay, it's fine. So if this had been truly symmetric, okay, in other words, it had been, for instance, quasi-geostrophic model with a rigid lid, then the bifurcation diagram would have been a pitchfork bifurcation, let's say mu, any parameter, which in this case is alpha t for alpha a equal constant, okay, would look like, thank you very much, Renee, okay, would look like this. Okay, so this would be the steady state, which loses its stability to, okay, so here you would have a perfectly symmetric solution, you know, the great anticyclonic subpolar gyre, and here a cyclonic subpolar gyre. Now the symmetry is broken and you get two solutions on these branches, so this becomes unstable and these take over the stability, in which, say, in one case it's this one which dominates, and in the other case it's the other one which dominates. So, you know, basically the mirror symmetry of this solution becomes the mutual symmetry of these bifurcated solutions. But this is not quite what happens here. So this would be, you know, essentially the normal form of this pitchfork bifurcation, okay, would be x dot is equal to x mu minus x squared. But if you have a perturbation of the symmetry, so you very easily verify that if you change x into minus x, you get the same thing. Let's say that you add here an x to the fourth with a small epsilon. What happens instead is, in the 5th century.
But the San Marlo people that went to the Malvinas were descended from the Welsh.
Well, that's quite possible. But anyhow.
So we don't mind the word Malvinas.
Okay. Okay. It was actually Bougainville, you know, of the Bougainvillea, whose task before going around the world was to turn over, you know, the King of France had sold it to the King of Spain, and he actually gave the keys to the Malvinas to the governor of Argentina, the La Plata colony at the time. Okay, good. So, okay. So now this is just to, okay, I'm a little bit slow here, but, you know, one of my teachers and then colleagues at the Courant Institute, Joe Keller, said you have to always start very slowly and then, so that at least for the first 20 minutes everybody follows, and then speed up so that you can lose everybody by the end of the talk. So I will have to speed up now. Sorry. So, okay, this is just because we still are at the Mathematical Sciences Institute. Okay, this is another intermediate model. This is now perfectly symmetric, now QG, equivalent barotropic, high. This is really high resolution, 10 kilometers. Okay, so you have pitchfork mode merging Hopf and homoclinic. In other words, we were even able in this high dimensional model to get the homoclinic bifurcation, which is notoriously hard to get because you might know that all these things, saddle node, saddle node, pitchfork, Hopf are what's called structurally stable. If you do a perturbation, nothing happens. Well, this, sorry, not pitchfork, the saddle node and Hopf, but homoclinic are structurally unstable, so they're really hard to get. Here are actually the pictures of how the solution, this is a computation of this unstable branch by the methods that you indicated. You see that it's still perfectly symmetric, but these are much more intense. Essentially, you can see that they're unstable to shear. Okay? So in some sense, this gyre mode is that destabilizes things here is a shear instability. And these are the mirror images that I was trying to do here. Okay? Actually carried out in great detail numerically. And this is the actual numerical solution. So you see how these limit cycles arising from the Hopf bifurcation grow and grow and grow until they give you this homoclinic orbit. And this is a 4 ODE model, which essentially manages to capture not just the pitchfork and the Hopf bifurcation, but even the homoclinic one. So it's a lovely piece of analytic complement to this. This is now, climbing up the hierarchy of models. This is actually something that Bo Chu handed me when I gave a talk about this in 1997 in Hawaii. So this is now a quasi-geostrophic model, but 2 layers, again, reduced gravity, 2 active layers sitting on top of a passive one, and still with the same idealized forcing. Okay, and here is a model-to-model qualitative comparison. Actually, Bo Chu's model had grid, mesh refinement in the interesting region and, much lower resolution, the so-called Sverdrup interior. Okay, and you see that you have essentially the same kind of behavior with this is a steady state solution, and this is now a model transport in the Kuroshio region, and you see that at least qualitatively they correspond to each other. You can also, he used some data to show that indeed in this case it is not. He looked at European Center reanalysis and so on and figured out that it wasn't the winds that gave you this interannual variability. Again, it is quite clear that on the seasonal time scale, the winds are important. These currents move, the Kuroshio extension and Gulf Stream move north and south with the seasons, but not necessarily so on the interannual time scale. So this is now a model to observation comparison. This is the spectrum, you see here the kinetic energy of a 2.5 layer shallow water model in a North Atlantic shaped basin dominated by a 7-year periodicity, and this is actually the axis of the Gulf Stream smoothed in a certain data adaptive way from the COATS data set, the Cooperative Ocean Atmosphere data set. So this is Gulf Stream axis data, and again you see that it's dominated by a peak at 7 to 8 years. Now again, this is based on some work with Vincent Moron and Robert Bottard using Met Office monthly mean SSTs for this century-long interval, and you see that there's a very substantial 7 to 8 year component in SSTs, which has some of the characteristics of this gyre mode with opposite gyre. So these are anomalies. You have to think about the anomalies of the gyre mode sort of going up and down. Okay, So now we're coming to more recent stuff. So I remember giving the talk up to this point, at some point at the ICTP in Trieste, and Shukla was in the audience, and he asked me, but what's this got to do with climate? And it left me speechless for a moment, and then I realized that what he meant was that, it's only the atmosphere that matters, okay? So the question is, do mid-latitudes sea surface temperature anomalies affect the atmosphere or not? And you might guess by now that I think they do, and I'm going to show you how. Okay, so this is now based on work of with Itzhak Felix and Eric Simonet, which was published in JAZ in 2004 and 2007, so first barotropic and then baroclinic. So there's a marine atmospheric boundary layer, and in the first paper there was just a barotropic atmosphere above, in the second there were 2 layers. And this is now a prescribed SST front, okay? And what happens to the atmosphere? Well, essentially what we found in this paper is that there are 2 components to the vertical velocity at the top of the boundary layer. One is this sort of what we call the mechanical component, and this is a thermal component that comes from the Laplacian of the sea surface temperature velocity. There's upward motion here with an anticyclonic gyre in the atmosphere. There's downward motion on the cold side with a cyclonic, again, gyre. And provided that the resolution is high enough. Now, I know that many of my friends would never believe that I would have said something like this, but we did in this paper. We especially tested that what we're talking about only happens when the atmospheric model has high enough resolution. Again, I have to remind you that this has been a big controversy. There's a nice review paper by Johanan Kushner, Walt Robinson, and many others that tries to summarize the literature. But there was a question about whether, as opposed to tropical SST anomalies, which by now we all know affect the climate, not only over the tropical Pacific, but in many other parts of the world, whether mid-latitude SST anomaly has an effect. And, well, the question was sort of left open. And our point in the first paper in 2004 was that the reason that was not consistently observed is because the GCMs which are used to answer this question had too low a resolution, 200 kilometers or above. Okay?
Already permitting almost.
Right. Okay, because when you try to do climate, one of the small disadvantages of GCMs, aside of having many semi-empirical or empirical parameters, is that you can't run them for very long at very high resolution. You need bigger and bigger machines, and you can't do many experiments with them, unless it's sort of a scattershot kind of thing like climateprediction.net. Okay, so if you have high enough resolution, you do generate this atmospheric jet from the SST front, which was prescribed here. Okay, again, as you enhance the gradient but still keeping it quite realistic, this jet becomes more intense. It loses its stability, first hot and then chaotic. But actually, this is an experiment in which we prescribed a 7-year periodicity to the intensity of the SST front. And this then is essentially the value of a stream function at the exit of the atmospheric jet. And you see that not only does the mean intensity of the jet change, but the particular instability associated with it. This is a 30-day periodicity and small amplitude. This is 70-day periodicity and high amplitude. Okay? So clearly this fact that that these western boundary currents change on interannular timescales can have a very substantial effect on the number and severity of blocks or zonal flow downstream, in particular over Europe. Okay, now it turns out that Shoshiro Minobe, who was aware of this work that we had done, but as he pointed out to me in January '09, didn't understand it, got a paper published in Nature, which is a marvelous paper, except for the fact that he doesn't cite this work. And indeed, he used the resources of the Earth simulator to have an atmospheric GCM at a very high resolution, okay, T239 and 48 levels. And this is observed rain rate. This is a so-called rain wall above the Gulf Stream and its extension. This is the rain rate in the AGCM. If you use a full resolution, this is when you smooth it. So basically you simulate when you do the things we said in '04 and '07, and you don't if you have lower resolution. Okay, in the meantime, we're also doing some work at the Laboratory of Dynamic Meteorology in Paris with a model. So they don't have these resources of the Earth simulator, but they have a model which allows a zooming capability. So there was a setup of 19 levels, 3 by 3 degrees outside the zoomed area and half a degree inside it, so about the right resolution. The zoomed area is essentially over the western North Atlantic, and perpetual forcing corresponding to February 15, 3 simulations, 800 days long, control with a climatological SST and no zoom, one with zoom and still the climatological SST field, and one with zoom and a stronger SST front. So this is the climatology. Okay, as you see, it's quite smooth. And this was, again, an idealized enhancement of the Gulf Stream front. And the result, so this is now a cross-section. Okay, this is the mean vertical velocity averaged between 70 and 40 west. And so this is height versus latitude. And red and blue mean positive and negative upward velocity. You see, this is the smooth one, nothing much happens. With zoom, it becomes slightly more intense. And with a zoom and with the SST front, it becomes even intenser. Yes?
What's plotted?
What's plotted, again, is the vertical velocity averaged in longitude between 70 west to 40 west.
The red means it's up large scale.
It's going up, yeah. And blue, it means it's going down. So there's a certain, so this is essentially what was predicted in that schematic diagram that I showed you at the beginning, and it actually happens. Now, you know, some data analysis, atmospheric and oceanic. Again, I'm speeding up, okay? And this is now, instead of the coads that we used before, this is a so-called SODA reanalysis, simple ocean data assimilation of Jim Carton and an associate. So this is now this is again, what we will show is a rectangle over the western North Atlantic, 28 north to 42, 80 west to 67, and 50 years of reanalysis from 58 to 07, okay? So what you see here is, and again, many people here do know these kinds of data adaptive spectral methods that we've been using. Others don't, but they can just go to the TCD website at UCLA. We use singular spectrum analysis, which is essentially this data adaptive advanced spectral method. What you see here is in the middle is the SST mean, and what you see marching around is a 7 to 8 year mode in the oceanic data. Okay? So essentially you see that, again, a lot happens, you know, along the western boundary of the North Atlantic. You see, maybe the easiest is to look at this here. There are strong positive anomalies, and here sort of in the opposite corner, there are anomalies of the opposite sign, and the same sort of thing that happens in the SSH field. Again, the mean is here, so you see very clearly the Gulf Stream extension, which is a mean over 2 different things, the North Atlantic drift and the Azores current, so you know it's a smooth field. And again, you see here a very strong positive anomaly and the anomaly of the opposite sign in the opposite corner. Okay, so this is now just the analysis of the SODA data. Okay?
How many years of analysis?
50. So you have essentially 6 or 7 repetitions. And again, SSA does pretty well if you have more than 5. Okay? Okay, this is just to show you, this is now Francisco Dron, who has been trying to complete this work with the LMD Zoom as Sidonie Brachet moved from Paris to Brest. This is just, trying to look at the issue of who, the tail and the dog, okay? This is looking at 4 points in the North Atlantic. This is, again, just some data analysis. And so all of these are in the Sverdrup interior except this one. Okay, here is Cape Hatteras. Okay, and he's looked at the lag regression of the SST. So this is well, he said regression. It should really be correlation. I'm sorry. This is the autocorrelation of the SST itself. And in red, you have the cross-correlation of SST with air-sea fluxes. And you see that essentially in the Sverdrup interior, where the nonlinear effects are not important, the inertial effects are not important, indeed, it is essentially the ocean that lags, the atmosphere that leads, except at point 2, where things look quite different. So in other words, in the western boundary currents. This is also an indication from a paper by Mosdale et al. Looking now at the simulation with a HAT-CM model. Large models are not all bad. They also have good things. And so you see, it says, where does SST add information to knowledge of the current NAO value? Well, it's obviously where you would expect after everything I've told you so far. And now comes really the thing. This paper was accepted finally last night. Okay? I was sitting in my office completing this talk, and I got a note from the editor, okay? And what do you see here? Okay, this is simulating the atmospheric response to SODA data, the 50 years of SODA data over the Gulf Stream region using the Felix Gil-Simonet baroclinic model. So it's a big beta channel, much bigger than the North Atlantic, of course, which you force with this stuff rather than with that constant SST front or this SST running a 7-year cycle, which I showed you before. So you use the essentially -5 meter data from the SODA analysis, use this, and the figure shows the NAO index computed in the model as close to what is done in the observations as possible. And this is now just a 12 months. So again, the simulated is solid, the observed is dashed. This is just a 12-month running average of the two. This is a 7 to 8 year mode. You almost cannot distinguish them by the eye. And these are 2 other modes, 2 and some years here, and 5.4, but these are smaller invariants. So again, you see that there are interdecadal changes in what happens to the NAO index and to the other components as well. But essentially, this sort of intermediate atmospheric model manages, forced by the SODA data, to track the NAO index almost perfectly. Okay, now coming back to the the LMD Z for the Americans, okay, model. Essentially, you can see here is the evaporation. So remember the idealized pattern of the SST front. Oops, sorry. Okay, yeah, okay, this was it. So, this is this slightly idealized formulation, strengthening of the SST front, and okay, here we are. Okay, you see, this is the evaporation, this is a sensible heat flux, and this is the precip. So, exactly what you expect. So conclusions, still have 5 minutes to go. Is it the tail or the dog? Okay, so what do we know? There's an NAO and it's important. It has decadal or near decadal variability, 7 to 8 years. It's an oscillatory mode, albeit weak, but can still help prediction, especially if we know how to use it. What do we know less well? Well, how does a climate system really work? I must say that I can't help adding this question. You know, there are certain statements on the websites of certain academies about the fact that the problem has been solved. Okay? Yeah, it says so because of the IPCC and, you know, the fact that various countries now have ministers of climate change. I would like to, you know, ask some of those ministers whether they know what the hell they're talking about. But there are statements, there is a statement in the community that the problem has been solved.
I thought they were just saying that we know that human-induced climate change is almost certainly a serious problem. And that the paleo record says that very well.
Well, no. I'm not a naysayer, Michael. I'm not a naysayer. Please understand.
That's all they meant, wasn't it? They don't claim.
Well, that's not what the public understands.
Oh my God.
Okay? What the public understands is that the problem has been solved. And, you know, many colleagues will say it that way. So I would like those people to explain to me the general circulation of the atmosphere and of the oceans.
Michael, you can't blame the science academies for giving the public that impression, can you?
I think I am blaming colleagues who are more concerned about modifying behavior than with the real science. Okay? I've grown up under communism and I'm allergic to people who try to modify behavior. Okay? I agree that, you know, I publish papers in Nature and Science saying that the temperatures are going up, and I believe that we contribute to it. But I'm really allergic to the statements about the climate being solved, the problem being solved. So, you know, is it the tail that wags the dog, i.e. weather noise that drives the passive ocean, or does the dog bite its tail, i.e. coupled ocean-atmosphere modes of decadal variability, or does the old dog ocean plane wag its tail, the atmosphere?
We picture two dogs with each one biting the other.
Well, now you're constructing an intermediate model.
Yeah, it's a toy dog.
Toy dog. Okay. So what to do? Well, work the model hierarchy and the data, of course. And I'm just going to leave you with some references. So this is the paper just got accepted last night, the atmospheric circulation over the North Atlantic induced by the SST field. This is a paper which is in press. I think last I looked, it was still on the early online release. And this is, of course, the counterpart of Lorentz 63 for the oceans. Thank you very much.
That's the same Andy Robertson who helped us with our...
That's the same Andy Robertson, you know, who has, I forget exactly how many hundreds or thousands of citations, okay, for his thesis. And I actually, since you're here, I would like to ask you, are you really the one who suggested that the order of authors be alphabetical?
I tried to maintain that throughout most of my career. I only got my name last these days.
Well, I know that, you know, of course, I have a PhD in mathematics and I'm familiar with that convention, but it is not the one which is used in general in our field, you know. I usually let my PhD students be first on their thesis, but anyhow, it's a very important paper.
Well, good for you. I mean, I hate the first author cult. It's very corrosive to good science.
Well, I know, but you can't help it. You know, it does change their careers. I mean, okay, well, okay, yeah, it's the same Andy Robertson. He was, you know, after being a postdoc of Joe Egger in Munich and of Claude Franquignoly in Paris, he was my postdoc at UCLA, and then a researcher before moving to the IRI at Columbia. And he's a great guy.
Please give him my best.
I certainly will, but I would also like to get him elected a fellow of the AMS, and if you could help, I'd be very happy. Okay.
There's been some discussion in the past about sort of the decadal variability of the Atlantic in terms of moving the gyre circulation, taking of order 10 years,
Yeah.
move the heat anomaly around
Yeah.
or whatever. But this is distinct, isn't it? This is about sort of Gulf Stream location,
Well,
guiding the jet stream.
yeah. You know, in oceanography, there is usually a distinction made between this wind-driven circulation, which I discussed here, and the so-called thermohaline circulation. What was called the Great Salinity Anomaly in the subpolar North Atlantic is thought to belong more to the thermohaline, but I always like to point out to my students that, you know, a particle of water doesn't know whether it participates in the wind-driven or in the thermohaline circulation. And, you know, it's of course three-dimensional motion, and again, disentangling what the more important effects are is very difficult. Just a second. We had a paper with another student of mine, Fei Chen, two papers in the mid-90s, 94 and 96 in JPO, I believe, where we showed very clearly that we had sort of an idealized, North Atlantic basin. I mean, we used this MOM from GFDL, but in a slightly idealized configuration. But we did show that there's a lot going on in the northwestern corner of the domain. So I can't tell you right now whether the Great Salinity Anomaly is or is not, you know, related to what I'm talking about. It might not be. I haven't looked at that. But I should say, you know, just one more moment, that we really think that where the gyres, you know, if you want to have this idealized consider spherical cow view of the North Atlantic circulation, where the double gyres meet is not at Cape Hatteras, which is where, you know, traditional physical oceanographers really think about it. It's you know, out the Grand Banks. Okay, so this would suggest that, you know, this sort of thing has some effect on things like the Great Salinity Anomaly. But again, I don't want to go too fine. Sorry. Okay. Yeah, I think Joe was.
So I thought John's question was related to whether or not the mechanism was distinct from the Saravan-McWilliams mechanism.
Well.
Versus the gyre instability.
Well, this is clearly different from both Saravan and McWilliams and Nealon and Weng, or Weng and Nealon, I forget. You know, it's again the situation. Since the North Pacific is a much bigger ocean than the North Atlantic, it's probably true that in the North Pacific, you know, westward Rossby wave propagation does play a role. But again, you know, it's not clear in the picture of refined mesh of Bochu, you know, what exactly pertains to the inertial effects. And I remember that at this workshop in January '09, there was some Japanese guy who gave me a reprint, but unfortunately he only gave me the paper. And you know, these days you lose the paper. And they did some sort of ocean GCM study in which they showed that both mechanisms seem to play a role. So, you know, you can easily see that the inertial stuff in where the mesh is tight interacts with this Rossby wave propagation in the Swerdrup interior. Oh, Tim.
This is more a couple of comments, I suppose, but it's a slight question, but there's a couple of things that you said resonated very much with me in a positive way. And one of them was about this issue of resolution, model resolution. And it reminded me, back in the, I think it was the early 80s, I did a study with actually a Chinese visitor at the Met Office at the time called Sun Xiaobo, where we were looking at precisely what you were talking about, impacts of sea surface temperature anomalies in the western North Atlantic on atmospheric circulation. And it was motivated, by the way, by the fact that some of the older generation Met Office monthly forecasters used that actually as a predictor, western North Atlantic at the region of the Gulf Stream separation. They used that as a predictor for central England temperature. So there was some evidence that there was a connection there. So we tried to see whether there was any dynamical explanation for this result and got some very strong positive results. We had a very strong impact in the model that we used. And we had a lot of flack from other colleagues around the world who tried to also look at impacts of SSTs in the Atlantic, on the Atlantic atmospheric circulation, and couldn't see anything. And it turned out the model that we were using was...
But is this result you're referring to published? I mean,
It was published in the Quarterly Journal in about 1983. I can give you the
yeah.
reference. And what we found was that we were using actually what was actually quite an old model, which had a hemispheric wall on the equator. But as a result of, and it had not terribly good vertical resolution, but because of the wall, we actually had relatively high resolution compared with the kind of emerging generation of T21R15 global GCMs. So we probably had 3 or 4 times the amount of resolution in that crucial area. And I certainly cited that and some of the sort of eddy dynamics as a crucial factor for why we got such a clear result when the other models didn't. I think the other thing, by the way, is a lot of these other models, the other thing you have to be careful of, if you have an observed sea surface temperature anomaly, which is manifesting changes in the winds, and your model itself has a bias in the jet stream, so it sort of pulls the jet stream away from where those SST anomalies are, you're not going to get the right response to those SST anomalies. So that's a kind of thing. So I was kind of quite pleased to see this because it sort of reinforces well.
Actually,
the only comment was that the response that we got to these SST anomalies, it had some projection on the NAO, but it wasn't, I wouldn't say it was primarily the NAO it projected on. So Mike Wallace, who you mentioned, has a number of these kind of teleconnection patterns. And we actually found one, I think it was called the East Atlantic or something, teleconnection pattern, that actually had our response had a stronger projection on than the NAO itself. So, you know, there's a bit of that. The other thing, just
I remember very well all those, you know, dipoles and wave trains
I'll
and so on.
send you the reference.
Please
By
do.
the way, just tangentially, I agree with your remark about I think it's been counterproductive, a lot of the community saying that the climate change science is done and dusted. I think that's done with great harm in many respects.
And I'm horrified to hear that anyone's saying any such thing.
It's unfortunately been the case, and I think it's done damage. And of course, if you read IPCC, it doesn't say that. The IPCC is quite careful about explaining the
Nobody reads really the IPCC. I mean, you know, it's very interesting that actually Uriel Frisch, who you know, ran a big meeting on the Euler anniversary. You know, it happens that Euler did his fluid dynamics papers at the age of 50, so the tricentennial of his birth coincided with a quarter millennium from his fluid dynamical work. This paper was one of the survey lectures at this meeting on Euler. It's a special issue of Physica D. So Uriel, you know, read the summary for policymakers and of Working Group 1, you know, and the physical sciences one. He said, this is not terribly clear for somebody who's pretty educated like myself. Him. And, you know, I'm pretty sure that there isn't a damn policymaker, you know, who doesn't have a PhD in something that can actually make sense of what is written in that summary. So, you know, let alone the fact, I mean, Lenny likes to point out that the good fit that is shown in the summary for the simulation for the 20th century is shifted, you know, is based on shifting the means by as much as 2 degrees. And that is only said on page 837 or whatever of the report. So first, policymakers, let alone, you know, science reporters and you know, just the man or woman in the street can't read the policy, you know, the policymaker summary, but also that is not, you know, such a wonderful reflection of the full report. Yeah,
I showed that figure you're talking about in my talk last week.
Oh, okay.
Okay.
Okay. If you do, I mean, I would actually like, somehow Lenny promised at 1 or 2 meetings that he would give me that figure and the exact reference, the page number. And, you know, I'd really appreciate that.
It's not from, the figure is not from the IPCC. You won't find it in the IPCC at all.
Oh, I
I
see.
think it was reconstructed afterwards.
I see. Okay. Well, I'd like to really have the figure and the exact reference.
I have to say that my take on all this is to agree with Freeman Dyson that despite the best efforts, the climate models are pretty bad, actually, and that they're not even good enough to tell us whether the present state of the Earth system is going toward a new attractor basin like the Eocene climate. Because they can't do snow accumulation well enough, and they can't do ice flow well enough.
I always like to point out that they're a heck of a lot better than economic models, which policymakers do take into account.
Oh, that's
So, the state of our science is not that awful like the naysayers say, and Freeman is sort of on that side, okay? I tried to correspond with him, but he sort of had a little bit of a fixed idea about growing trees or something, so he wasn't that interested really in the climate science. But
he seems to say the models are lousy, therefore we should wait another century before.
No, we should not. That's exactly what I'm trying to say, that economic models which are incomparably lousier.
I agree.
I mean, I'm trying to do macroeconomic modeling, and I have some papers published in respectable economic journals, and I can tell you that the models which have been used for impact studies, are essentially AR1. What's called so-called real business cycle models. They're called real not because they're real, but because they don't take into account monetary aspects. So-called real business cycle models are supposed to be driven by residues of changes in productivity and so on. This takes us to can we talk about the science? Sorry, this always gets deflected into the policy. Some of the less prominent members of the audience, if I have said anything to you that is of interest but not clear, would you please? I was telling Michael.
Did you? Sorry, just one question from the NAO index, which you showed at the beginning. Is there evidence from that of this 7-year periodicity?
Oh yes, of
Did you
course.
show that?
That was, I didn't show it here, but even Carl Wunsch, there are many references, and you can find them in any of those papers, but even Carl Wunsch, in that famous paper in which he said everything is noise, okay, and you guys don't know how to do spectral methods, except that he's still doing the spectral methods that he learned in kindergarten, even he admits that there is a bump at 7 to 8 years. Okay, it's in the BAMS paper, 98 or something, whatever. So that's okay. But what I'm saying, it's quite clear that that peak is not as big as the quasi-quadrennial and quasi-biennial peaks in the SOI. Okay? So probably there's less predictability. I mean, even for ENSO, for which there was a special program that cost, I don't know how many tens of millions of bucks, and that advanced our knowledge, our understanding of what goes on in the tropical Pacific and above quite a bit. Even there, with now a couple decades of experimental prediction, we can't very well go past 6 months. Okay? Well, various claims have been made, but there was a paper in Science by Doc Chen and somebody, Tony Busalaki, was going to go to 2 years, except we haven't really seen it. This is actually something that Tim Barnett pointed out to me when we became involved in experimental prediction by statistical methods, SSA and so on, that no matter how carefully you do, hindcasting, with no look ahead, the correct kind of retrospective forecasting or whatever, when you start going into real time, something very strange happens. Okay, and that has happened to Doc Chen and to everybody else. So.
It's like